Hello everyone. So we are proceeding with our discussion on dynamic analysis for the continuous time case. We are going to discuss differential equations now. We use the method of integration to solve differential equations, and we will only consider the case of a first order linear differential equations over here. So let's look at some of the definitions first. In simple words, a differential equation is an equation which contains the derivative of a variable with respect to time. So the investment equation we discussed in the previous video, which was di over dt is equals to 4t cubed, was indeed a differential equation. Here the variable investment was written as a function of time. Other example could be like this, where it is given that the investment has a rate of change of 20. And if, for example, we know the initial condition that at time t is equals to 0, investment has a value of 100, we know at time t is equals to 1, investment would be the base value plus the rate of change, it would be 120. That could be another example of a differential equation. Yet another example could be like this, or like this, where time appears in a square term. Objectives remain same, that we want to find out the time path of the variable. In that case, we only see investment. It could be that we have more than one variable in a differential equation that we're going to see later. Another objective is to find the equilibrium value if it exists in the long run. And by long run, we mean when t approaches to infinity. By degree and order, what do we mean by that? The order of a differential equation is essentially the highest order of a differential appears in an equation. For example, over here we see the derivative, it contained a first order differential. So we will call that a first order differential equation. And over here, as we can see, the highest differential appeared in an equation was second. So we'll call that a second order differential equation. The degree of a differential equation is the highest power of a differential. In this case, the degree would be 3. So this equation would be of second order, third degree. The differential equations could be linear and non-linear. A non-linear differential equation could be where the differential, which is di over dt, appears as a multiplicative form of I over here. So this differential equation would be of order 2 because it essentially contains second order differential, of degree 1 because the highest power of a differential is 1 in this case. So it would be a nonlinear second order first degree differential equation. And again, we will use the method of integration that we studied to find out the solution. Another example of a nonlinear differential equation would be where changes in capital stock is written in this form, which is that changes in capital stock would be the savings that were made in the previous period minus the depreciation. So now we are going to see how we can find the solution of that differential equation. That is our objective, and we will assume a differential equation of this form. Let's just assume that we are given this differential equation when we want to find its solution, and which would be as a function of time only. The solution will contain of two terms, or we can say two sub-solutions. One we will call the complementary function, and second is what we'll call the particular function or the particular solution. And the sum of both will be called the general solution. The particular solution can be considered as the value which the variable reaches in the long run. And the complementary function will be the deviations from that equilibrium value. So let's just focus on the complementary solution or the function first. To get the complementary solution, we always set the equation constant equals to 0 and then use the integral calculus tool that we just reviewed in the previous video. So this is the differential equation. What we have to do is to assume this constant equals to 0. Our differential equation will become dy with dt plus 2i is equals to 0. And now we will use integral calculus to find its solution. So let's just do a little bit of transformation of this equation. If I can write this equation like this, the next step would be I can write this equation as di on this side and dt on this side, and then I can proceed to apply the integral on both sides of the equation. And as we know, the integral of 1 I would be log of I, and in this case it would be the it would be multiplied by t. So we will have the integral solution as this. The next step would be to apply the exponent on both sides, and we will reach to this step. Log and e would be cancelled out, and finally we will reach to this solution where we sort of saying that e raised to the power c is equals to a, because e raised to the power c would be just a constant, so we're just assuming it equals to a. And now we are focusing towards the particular solution or the particular function of this differential equation. Since the particular function or the particular solution is the value which the variable reaches in the long run, it means the variable would stop changing at that time, which means this differential would be equals to 0. Say I is equals to z, then di over dt would be equals to 0. Over here, z is just a constant that we're assuming. So let's substitute this value over here. For I, we will substitute z, and di over dt will substitute 0, and then we will get the value for this z. This long-run solution, a particular solution, is also called a steady-state solution. And now we have reached to the complementary solution and the particular solution, and then we're going to just add them both together and we will find the general solution. And general solution in this case will be a e raised to the power minus 2t plus 3. So we were given a differential equation in this form, and then we reach to its solution of a general solution. And now we are only one step away from completing that solution. That is, we just have to find out the value for a. And again, that we will use through using the initial condition. Those should be given to us. So let's just do this. The way we do it, again, the same that we did before. We substitute t is equals to 0, and when we substitute t is equals to 0 in here, we obtain this expression. For I at time t is equals to 0, we know the value is equals to 100. So we'll substitute that value over here, and we will get the value of a as 97 upon simplification. Notice that we substituted t over t, we substituted 0 for t over here as well. So we now have a value for a, and we're going to substitute that into the general solution, and our general solution will look like this, where, as you can see, everything again is either a constant, or in the case of exponent we know its value, and only thing that we know that is a variable is t. So if we substitute any value for t, we will get the value of our investment for that point in time. So we can find out the value of our investment for a given point in time. So now the second objective was to know its long run equilibrium value. For that, we will substitute t as infinity over here, because as time reaches to infinity, whether that investment reaches to a particular value or not. So we'll substitute that, and when we substitute t is equals to infinity, what we get is that I would be equals to 3. So in that case, we know that in the long run, investment reaches to its particular value or an equilibrium value of 3, or it's a steady state value as 3, and we we know its time path as well. And if you want, we can plot this. It would look like this. What would happen if that coefficient of exponent was not negative? Because for this convergence to happen, this coefficient has to be negative. In case if it's not negative, for example, if we say it happened to be, instead of -2, had it been +2, we would have a graph something like this. Now, as you can notice, in this case, we are not reaching to an equilibrium value in the long run. So although we can find out the time path of that variable, we know that this would not converge to a value in the long run. So we solved a given differential equation, we reached to its general solution, and we looked at its convergence in the long run as well. Okay, so now let's discuss the same concept in the form of difference equation. The difference equation is essentially, it represents the same phenomena of modeling the change in the variable, but in this case, we will consider time as a discrete variable. I mean, the case might appear more close to reality as we observe data in discrete time for most of the economic variables, especially which are related to macroeconomics. Again, our goals remain same, that we want to find out the time path and we want to see if they converge or diverge in the long run towards a particular value or not. Since time variable now can only take integer values, so we will represent di over dt as delta I over delta t. In case of differential, we know that change is very small. Over here, we are considering the change of time equals to 1, so we can use delta instead of the differential over here. Since we are comparing the values of I in two consecutive period in this case, so we can represent delta t equals to 1. Here, if we want to write down, we will see delta t equals to 1 implies delta I divided by 1 would be equals to delta I, which is another way of writing I of t plus 1 minus I of t, which is change in I over here written in the expanded form. So let's look at some of the forms of the difference equations. Again, we will only consider here single variable linear form of difference equation. The general method for solving the difference equation is similar to what we discussed for the case of differential equations, and that would be that they will be part of two solutions, one particular solution, another is a general solution. If, for example, we are given a differential equation of this form, overall solution, there would be a general solution would be composed of the complementary function and the complementary solution and the particular solution. And the interpretation of those solutions would also remain the same as we saw for the case of a differential equation. To find out the complementary solution, we're proceeding with the same method that we saw for the differential equation, that we are substituting c is equals to 0, and then we're going to solve for it in this case. For the case of differential equation, we could use integral calculus, but for the case of differential equation, we will have to rely on some other method. One method is we proceed from t is equals to 0, and then we proceed from t is equals to 1, 2, and 3, and we see what kind of solution form does it look like. If it is possible to write down I of t as some form of a constant or an initial condition, then we can use that solution. So let's see if at t is equals to 1, what would happen. So again, we are using an example of this differential equation where we are given a value of I of t plus 1 minus 0.5 I of t is equals to 0. I can write this equation like this form as well, and then if I substitute at t is equals to 1, I will get I1 0.5 I0. Again, I0 could be given to the model, so we kind of know this value, so we can write I1 as a we can know the value of I1 given we know the value of I0. If we iterate 2 times t is equals to 0, we can write down I2 is equals to 0.5 of I1. Another way of writing this is I can write I1 as 0.5 I0. Again, I see a pattern developing, which is that I write down I investment at a particular point in time as initial condition times multiplied by the coefficient which was attached to it raised to some power. So following this pattern, if I use t is equals to 3, I know it would be 0.5 times 3 times I0. Again, I am following the same method. So with this, we can now proceed on to for the value of time t is equals to t plus 1. For time t plus 1, we know that it would be the value of, it would take the value of 0.5 t I0. So we have now a solution form that we can try, which would be it is equals to a b raised power t. Again, a could be any constant or initial value, and b would be the coefficient which would be attached with the investment over here. In this case, it would be minus 0.5. So we will try this solution method over here, and we will, if it is equals to a b t, it plus 1 would be a b raised power t plus 1. And when I substitute these values in this general equation over here, where I would assume c is equals to 0, I get this expression. From here, I just have to take common a b raised power t and cancelling out this non-zero, I will get b equals minus a. So now I know that I can find the value of b in this case, which would be minus a. And a, as we know, is this expression, which would be the coefficient attached with the investment term, it term. And following this, we now have the value for the complementary solution. It would be a b raised to the power t, or a into minus a raised to the power t. Okay, so now let's move toward the particular solution. We have found the complementary solution. We know it looks like this. We know general solution is sum of these two. Now let's turn toward the particular solution. Particular solution finding is the same for difference equation as we found for the differential equation. The condition remains same that in the long run the variable stops changing. For the differential equation, we assume its derivative would be equal to 0. And for the difference equation, we would say that it would remain constant for all values of ITs. For example, it would be same for IT plus 1, IT plus 2. It's another way of saying that it would stop changing. So let's just move towards finding a solution, particular solution that we need to complete the general solution of investment difference equation that we started. And again, we are saying that if it is equals to z, which is a constant, it means it plus 1 would be also equals to z. So we are going to, it's another way of saying that its differential is equals to 0 and stop changing. So all we have to do is to substitute this z into the original difference equation, and once we substitute that, we get the value of z plus az is equals to c. From here, we need to find the value for z. Once we find it, that would be our particular solution. Notice that c would be given to us. It's a constant from the difference equation. A is the coefficient of the it term. So everything is known over here, and we find the solution, particular solution for this difference equation. If we want to use this particular solution to finish our overall solution would look like this. Let's just take an example of the difference equation and we'll substitute the values over here, that for the A, C, and then to develop better idea for this. So we started with the difference equation where it plus 1 minus 0.5 it was equals to 0. And the value of A in this case would be minus 0.5. And for the complementary solution, we know that it is A into minus A raised power t. So once we substitute it, for A we substitute minus 0.5, it would become A plus 0.5. So now we have a complementary solution. For the particular solution, we are going to use this formula over here, and C value for C is 2, and once we substitute those values over here, we got the particular solution of 4. And combining both solutions, we get the general solution, which would be the sum of both solutions. We find the value of A through initial conditions, and everything else except t is known over here. For convergence to a certain value in the long run, which is as like t tends to infinity, the term 0.5 raised to power t, this term has to reduce to 0, which is only possible if the value of this coefficient a falls in a certain range. And that range is that it has to be a fraction, it has to fall between minus 1 and 1. So if that happens, we'll have a convergent solution. Any value of a outside this range, we will not have a convergent solution or a dynamically stable solution. So with this, we can stop over here, and in the next video, when we will see the optimization and the discrete and continuous time case, we will see how we end up with those difference and differential equations at the first place. Thank you.